Okay guys, on to section 7.3 logic. Okay, so this section, not too long, pretty short and sweet. Get in, get out, get on with the rest of your life. And basically what this chapter is doing is setting up some ideas that we're going to be using later, right? Some definitions, a lot of definitional kind of stuff. So it's important that you take your time to read through the slides, read the text, check out the video a couple times if you need to. So that way you understand the basics of what this section is talking about, because you're going to need it for the next several chapters. Okay, so we introduced previously the idea of knowledge bases, and these knowledge bases are they're like databases of sentences. Okay, and so these collections of sentences essentially are defining what a logic agent knows. Okay, and so sentences that belong to these knowledge bases, they have their own rules, they have their own syntax for how they're written, just like any programming language. Okay, so when the sentences are well formed, they're following the syntax for the representation language that you're using. So an example from arithmetic: x plus y plus z equals 14, right? Now it's not a programming statement, just remember, basic old arithmetic. You know what this means because there's a syntax for this sentence, right? The representational language is arithmetic, or the symbology, is that even a word? How you symbolize, what this means. Take whatever x is, add that with y, and then add that with z. The sum of x, y, and z is going to be 14. Okay, so there's a syntax there that says, well, plus and equals are used in a particular way, in a particular order. When you're specifying these different variables, you combine them in a particular order, and that tells you what the sentence means, right? Or I say means, right? But we're going to talk about meaning here in a second when we talk about semantics, right? It's just, you can read it if it's written correctly. Okay, think of it that way. Now, the semantics also need to define. Now, semantics, that is meaning, right? So x plus y plus z equals 14, that's syntactically correct for arithmetic to mean, the sum of x, y, and z is 14. But the fact that x plus y plus z means the sum, right? And then the equals means equivalent to or is equal to, right? And then 14 represents a quantity. That's the semantics of that sentence. That sentence means the sum of x, y, and z is 14. That's the meaning. Okay, that's the meaning of the sentence. The way it's formed is following the rules for, writing arithmetic expressions. But what that sentence actually means, that is the semantics. Okay, so that's going to define truth, right? What something means is going to help us to define the truth of a sentence. Okay, and that truth is going to be defined with regards to each possible world. Okay, so when we talk about each possible world, we're talking about a model. Okay, so you have a model which is basically just going to be a collection of variables that are assigned truth values. Okay, true or false. And the particular configuration of those variables and their truth values assigned to those variables make up a possible world. Okay, so here's an example going back to arithmetic. X plus y plus z equals 14 is true, right? That is true if x is assigned 3, y is assigned 5, and z is assigned 6, right? So that sentence is true based off of the semantics of what it means to say x plus y plus z equals 14. If we assign to x 3, we assign to y 5, we assign to z 6, right? That is true, that is 14. Okay, now that is one possible world. That is one possible model. The assignment of 3, 5, and 6 to x, y, and z respectively, right? Another possible world or model, those terms are kind of interchangeable, would be if x was 0, y was 1, and z was 13, right? Then that sentence would be true because the assignment of those values to those variables equals 14, okay, based on the semantics of what that sentence means and the assignment of those values to those variables. In that possible world, that's one possible situation, one possible model, 0, 1, and 13. That's one. Another is 3, 5, and 6. Okay? So it is true that x plus y plus z equals 14 when x is 0, y is 1, and z is 13. It is true in another possible world, another possible assignment of values to variables, that x plus y plus z is 14 when x is 3, y is 5, and z is 6. So that's two possible worlds. Okay, two possible sets of values assigned to those variables. Now, in another possible world, the sentence is false if, in that possible world, in that model, x was assigned -1, y was assigned -2, and z was assigned -3. It would be false to say that x plus y plus z is 14 if x is -1, y is -2, and z is -3, because those things total up to -6. -6 is not 14. That sentence would not be true in that model, in that possible world. Okay, so possible worlds, when we talk about that, it's kind of similar to agent environments, right? What are all the possible states that an agent could find itself in, right? So, you know, it is possible that the agent could be in this particular state, or the agent could be in this other state, and this agent could be in this third state. Now, using the term possible worlds and models interchangeably, but models it's more abstract, right? So they're more of a mathematical construct, right? They fit more, using the term model fits more to when we're talking about x and y and z equal 14, right? And so a model, as I was just saying, all the possible values for a set of variables, right? So the assignments of these values to these variables fixes truth, right? Now, it's abstract because what is x, what is y, what is z? We haven't clearly defined that, okay? Now, as we move forward in logic, when we discuss logic, we're going to be using symbols that represent some aspect of reality or the environment, right? And we'll be assigning some value. And so the combination of values to those symbols is going to be describing the environment in some way, okay? And that's going to enable us to deduce whether or not there's a pit in that square, whether or not the wampus is in that square. It is true that there is a breeze in square 1, 1, right? And the player is in square 1, 1. So what does that infer? Right? That infers that there must be a pit nearby, right? So, you know, we're going to be using these variables and assigning them values such as square equals breeze, right? To determine or to describe something about the world, okay? Now, if you have some sentence alpha, and that's true in model M, then we can say that model M satisfies sentence alpha, right? So by model M, we mean a particular combination of values assigned to variables, where those variables are going to represent something about the possible world, about the model. Okay, so if we say M satisfies A, that means that that sentence is true. Whatever values we assign to those variables makes that sentence true, right? And those values assigned to those variables, that represents one possible model, one possible world. Okay, so another way of putting it is you could say M is a model of alpha, right? Or then you also can have this function notation where we have m and it looks like we're passing alpha as an argument to function m. So that means the set of all models of alpha. So in the previous example, when I was going through and I was saying, well, one possible assignment of values to x, y, and z was 0, 1, and 13. Another was -1, -2, -3. Another was, 3, 5, 6. Okay, so if those were all of the three possible combinations of values being assigned to variables, if that was all of them, if that was the only possibility, right, then this notation here, m, alpha, m of alpha, that would mean the set of all models of A. That refers to collectively those three combinations of values assigned to those variables. Okay, so let's talk about entailment between two sentences. What that means is that one sentence logically follows another, right? So we can write it like this, where we have alpha entails the sentence B, right? Sentence alpha entails the sentence B. It's kind of like this bar with an equals. Okay, so again, it's kind of abstract. It's an abstraction here because alpha, and beta could represent anything in some possible world. So, for example, maybe sentence alpha is 80 years old. Maybe that's what it represents, and beta is you're old, right? So what this is saying is, hey, 80 years old entails the fact that you're old, right? So one sentence logically follows from another. You're 80 years old, therefore you're an old person, right? And I'm not trying to be ageist here or anything like that. That was just the first thing that came to my head. Now, formally, we can say that alpha entails beta if and only if, for all models where alpha is true, beta is true too, right? So this is kind of like logical if, right? Truth table for logical if. Okay, so alpha entails beta if and only if, for all models where alpha is true, right? Then beta is going to be true also. Okay, so here's another way of putting it: alpha entails beta if and only if. The set of all models for alpha is a subset of the set of all models for beta, right? So remember what we were talking about, set of all models? Okay. So easy example, going back to arithmetic, right? So if x is equal to 0, then that would be our alpha, and that would entail that x times y is equal to 0. So x times y equals 0, that's our beta. So it logically follows, if x is 0, well, 0 times anything is going to be 0. That just makes sense. It's logical. It follows. So let's look at another example. Let's go back to Wampus world, right? So there's our legend again. And remember, Wampus world, 16 square board. Okay, and we got the agent in square 2, 1. Okay, and square 1, 2, 1, 1, 2, 1, all okay, right? The agent has determined up to that point that we're fine, right? But one of the percepts is that there's a breeze. There's a breeze in square 2, 1. Now, it follows, it entails that there must be a pit in either 2, 2 or 3, 1. Agent in 2, 1, breeze, it logically follows based off of the rules, based off of what we understand, based off of our knowledge base, that there must be a pit in 2, 2 or 3, 1. Okay? So, now, does 1, 2, does 2, 2, does 3, 1, do those have pits? Maybe, maybe not. Okay? So, it's all going to be based off of what values we assign to certain variables, right? So, is there a pit in 1, 2? Is there a pit in 2, 2? Is there a pit in 3, 1? Okay? Now, assign, have some variable A represent 1, 2. Have some variable B represent 2, 2. Have some variable C represent square 3, 1. Assign P to 1, 2. And then no P to 2, 2, and 3, 1. That's one possible model. No pit in 1, 2, pit in 2, 2, no pit in 3, 1. That's another possible model, right? So we're assigning a combination of values to variables, right? Where A represents square 1, 2, B represents 2, 2, C represents 3, 1. Is there a P or is there not a P, right? 2 to the 3, or 2 cubed, possible models there, okay? Okay, so let's look at another example of this, figure 7.5, right? So we just said we could have 8 possible models based off of what we know so far, right? So what's the subtitles, or what's the description here say? Possible models for the presence of pits in square 1, 2, 2, 2, and 3, 1. The knowledge base corresponds to the observations of nothing in 1, 1 and a breeze in 2, 1 is shown by the solid line, right? So what does that mean, right? So these are the possible models, right, of what happens if we've got breeze in 2, 1, everything's inside the solid line, and we know that there's nothing in 1, 1. We've observed nothing in 1, 1. So that's one particular combination of values assigned to variables, okay? So where each variable is basically one of these squares, right? All right, so the dotted line shows models of sentence alpha sub 1, which is to say there's no pit in 1, 2. Okay, so all of these, right, inside of the dashed line, right, this is what it would look like. This is what the combination of values of variables would look like if there were no pits in square 1, 2, which is 1, 2, this right here, 1, 2, 1, 2, 1, 2, 1, 2. The rest of them have pits in 1, 2, so we can eliminate those. Those aren't possible. Those aren't these are not possible worlds, okay? So these aren't models that we're going to be looking at. Now, for B, the dotted line shows the models of alpha sub 2, which is to say no pit in 2, 2, right? So no pit in 2, 2, no pit in 2, 2, no pit in 2, 2, no pit in 2, 2. So we're making two statements about the world with alpha sub 1, alpha sub 2, two sentences. We have to evaluate truth, right, of those sentences. Okay, so there's two possible conclusions, right? Two possible conclusions. We'll come back to here in just a second. There's no pit in 1, 2, or there's no pit in 2, 2, both surrounded by the dotted lines, as I was just saying. Right now, by inspection, for every model where the KB is true, alpha 1 is true. That is to say that for every model where our knowledge base is true, there is no pit in 1, 2. So let's go back up here and look, right? This is alpha 1. Here's our knowledge base, okay? So this is true because in our knowledge base, no pit, no pit in 1, 2, no pit in 1, 2, no pit in 1, 2, okay? And in this possible world right here, no pit in 1, 2. Remember, we could eliminate these other ones, okay, these other possible models for reasons I just said. Now, let's go take a look at, alpha sub 2, there's no pit in 2, 2, okay? Now, if we go back up here and we look at all the possibilities where there's no pit in 2, 2, right? That would be no pit there, no pit there, no pit there, no pit there, okay? Now, that is going to cause this is going to be invalid, right? It's not going to follow because we know that there could be a pit in 2, 2, right? Because of the fact the breeze implies that there could be a pit in an adjacent square, right? So that sentence alpha sub 2 that states no pit in 2-2, that doesn't entail, it doesn't follow, it doesn't make any sense. Because based off of our true knowledge base, there could be a pit in 2-2 because that breeze in 2-1 implies there can be a pit, right? It's a possible valid assignment of a pit to that square, right? Pit to variable square. Okay, so alpha 2 is not entailed by the knowledge base in that case. Okay, so the agent can't conclude that there's no pit in 2-2. So lots of math there, but it just means, look, it's impossible for there to be no pit in 2-2 because we detected a breeze in what was it, 2-1, right? That's all that means. Okay. Now, I mean, it's a lot of fancy language, a lot of fancy, little bit of math there, but it's just like, look, we know that if we have a breeze in a square, that there must be able to have a pit in one of the adjacent squares. Okay, and so it's just an example of reasoning using mathematic notation. Okay, now knowledge base could be multiple sentences or one giant sentence describing everything. Hanks and Martinez. That's one fact. That's one sentence. You're watching this video. That's another sentence. CSUEB is in Hayward. That's another sentence, right? So that's one possible way. Okay, that'd be one knowledge base, one set of sentences. Or instead of having those three sentences, instead of having multiple sentences, the knowledge base could be one giant sentence describing everything that could possibly be. So instead of having three separate sentences, we could have one sentence that says Hanks and Martinez, and you're watching this video, and CSUEB is in Hayward. Okay, so you could construct your knowledge base in multiple ways. Now, the knowledge base is false if it's in contradiction to what the agent knows, right? So, false. If 1-2 has a pit, that's going to be, we're going to have a false situation because there's no breeze in 1-1, right? So, no breeze in 1-1, that means that there has to be no pit in 1-2, false, okay? So that left us with just the three possible models with the true knowledge base in our previous figure. So as I was saying, we saw an example of entailment, right? We did logical inference. Okay, we came up with some conclusions. We derived conclusions. We manufactured conclusions based off of all of the possible configurations of values to variables. What we were doing is we were going through and performing an inference algorithm where we considered all the combinations of variables assigned values and checking those against some statement. We're making some statement about the possibilities. Okay, so what is this known as? This is called model checking, right? So why? Because you go through all of the models and you see if your sentence is true for all of the models or your knowledge base is true. So entailment, you got a needle in a haystack, right? So you know that there's something in the bigger picture, the bigger pond. Inference is finding that thing, okay? So the set of all consequences, that's the KB haystack. That's the knowledge base haystack. And then the sentence is the needle, right? So here is some notation for you, right? And so what this is saying is alpha is derived from our knowledge base by I for some reason, right? And that reason is being represented by I. So we can derive our sentence alpha from our knowledge base because of something. And that something we're just calling I, okay? All right, so sound or truth-preserving inference algorithms. Any algorithm that is sound or that keeps the truth or that preserves truth, doesn't distort things, that doesn't just make stuff up. Any algorithm that works correctly is going to derive only entailed sentences. Complete inference algorithms will derive all possible entailed sentences, right? So the sound or truth-preserving ones are going to derive only entailed sentences, One thing logically follows another. And it's complete. That algorithm is complete if it can derive, if it can produce, if it can construct all the possible entailed sentences. Following this reasoning that we've just been discussing, the conclusions have to be true in any world where the premises are also true, right? So if you've got some premise, alpha, and that leads you to some conclusion, beta, if the premise is true, if alpha is true, if it is the case that you're 80 years old, then it must follow, it must be true that you're old. Okay, so here's a quote from the textbook. The knowledge base is true in the real world, then any sentence alpha derived from the knowledge base by a sound inference procedure, by a sound inference algorithm, is also true in the real world. Okay, so we got syntax, we got semantics, we got inference, we got algorithms. Okay, figure 7.6 is just saying, or trying to demonstrate, look, you've got these sentences, they mean things, right? And what you're doing with those sentences is you're representing something, right? Those sentences have meaning. Okay, if you have sentence alpha that entails sentence beta, right? Alpha means something, beta means something. That's representation. That's the abstraction. In the real world, whatever they're representing, and by real world, I mean, it could be the real physical world that you and I live in, or maybe an environment that an agent is operating in, right? So a sentence is going to correspond. It's going to mean something in the real world, okay? And so if the representation is of that sentence, or if that representation, if whatever it is, that premise, if that's true, then it must be the case that what follows, what entails, is true. So a sentence that entails another sentence, in the representation, we use that language, those sentences mean stuff in the real world. In the real world, you're saying, well, there's some aspect that follows from some other aspect. Alpha entails beta. Okay, my alpha, real world, 80 years old. That's one aspect of the real world. So it follows that beta, you're old. So what about grounding? Okay, grounding. So when we talk about grounding, we're talking about logical reasoning and how it's going to impact the agent's environment. It also has to do with how can we tell that a particular knowledge base is true in reality, right? There's this abstraction that knowledge base is representing. The wampus is in a particular place, the breeze means something, you got glitter in a square. How do we know that knowledge base is true? Answer, sensors. How do you perceive the world? In wampus world, agent could smell, right? So that agent program, it's making its sentence. When? If the smell sensor smells something, right, there's a sentence that's getting generated. That sentence is getting added to or being examined against the knowledge base. If that sentence is in the knowledge base, then it's going to be true in the real world. Okay. So what's learning in this context? Okay, you got rules that are used to create a sentence, right? And so the general rules used to produce a sentence is gonna, so these rules, they might exist prior. So breeze, there's a pit nearby. That's one general rule. You can create new rules, right? So as I was saying, as you're creating those new rules dynamically on the fly, you're learning, okay? So could be the case that wampuses smell every day, but leap year, right? So that's a new rule that maybe was added as the agent was going about its business. Next up, we're going to talk about propositional logic, a very simple logic. We're going to introduce some rules. We're going to introduce some symbols. We're going to introduce some operators, and we're going to see how they work. And we're going to use these tools to implement the ideas that we got an overview of in section 7.1 through 7.3.